Hello to the attendees. My name is Albert Cohen, chair of FoCM. I want to welcome all of you to this first session of our online seminar. So, as most of you know, FoCM is a scientific society that promotes high-level research in areas where mathematics and computation meets, and there are many such areas. Their growing diversity is reflected both by the journal of FoCM and by its conference, which are usually taking place every 3 years. This year, last year in 2020, the conference was planned in Vancouver, but as many other conferences could not take place, a couple of workshops have been rescheduled online by their organizer. And in the fall, after a suggestion by Mike Schub, it was decided to organize this monthly online seminar with the plenary speakers. The organizer are Ben Adcock, Marcus Bachmeier, Evelyn Hubert, Agnes Santo, and myself. And we're extremely grateful to the many plenary speakers who have accepted, for most of them. And so today, we will have 2 lectures by Afonso, Bandeira, and Caroline Uhler. And the chairperson will be Agnes Santos, the former chair of FoCM. And I immediately give her the room. Please, Agnes.
Thank you, Albert. Hi. So thank you, everyone, for joining this FoCM online seminar. I was the previous chair of the FoCM Society until Albert went to the office this summer. So before I introduce the speakers, I would like to say thank you for the organizers of the FoCM 2020 conference, which was well underway when it was canceled in March. Let me share my iPad just to show you the conference website. So this was the conference website, and without saying all the names one by one, let me just show you how many people were involved in the conference organization. So I would like to say special thanks for the executive committee of the FoCM Society, to the local organizing committee of the FoCM 2030 conference, the workshop committee, and also to the workshop organizers who already did the job of inviting speakers, and also for the funding committee who they were very successful funding the conference. I would just like to mention that the next conference in 2023 will be also in the Vancouver area, so all this will not be completely lost, all this organization. Next, I would like to introduce the next speaker, who is the winner of the 4 Stephen Smale Prize. So this page that I'm showing is a page on the FoCM Society's website about the Stephen Smale Prize. So before I introduce the speaker, let me tell a few words, really just a few, about the Stephen Smale Prize. It was created by the FoCM Society with the objective of recognizing major achievements in furthering the understanding of the connections between mathematics and computation. This prize goes to a junior researcher within more or less 10 years of his or her PhD. And the first Smale Prize were awarded in 2011. It's always awarded at the FoCM conferences, so we couldn't award it this year because the conference was canceled. And I would also like to mention that the insignia of this prize is the Gumbirds, and it's sponsored by one of the creators, Gábor Domokos, and also by Otto Albrecht. And so let me show you an enlarged picture of these Gumbirds. You can read more info about it on the FoCM website. This is the one for the Stephen Smells Prize. These are not numbered, but specially created for this prize. And the one that goes to Afonso Bandeira, who won the 4th prize, is on its way to get to him right now. So we couldn't give it to him personally. It's not advised to mail it, so it's only on its way to a friend. The 2020 Smale Prize, the 4th one, had the following selection committee. I want to show you. So the selection committee was Annalisa Buffa, Gunnar Karlsson, Maria Caro, Hans Muntekas, Klaus Ritter, Michael Singer, and myself. And we received 12 extremely strong nominations of young researchers. And we had a really hard time and a long discussion choosing the winner, who is Afonso Bandeira, who will give the first talk. So let me introduce in a few words Afonso. He received his PhD from Princeton University in 2015 under Amit Singer, and presently he's a full professor at ETH Zurich. And the short version of his laudatio is the following. Afonso Bandeira has been awarded the 4th Smale Prize for his pioneering work on the foundations of computational mathematics. Bandeira is an incredibly productive and versatile researcher who has successfully applied and combined concepts and tools from optimization theory, probability theory, information theory, statistics, theoretical computer science, harmonic analysis, and number theory to design and analyze, to the design and analysis of algorithms for solving real-life data science problems. You can read the full laudatio for Afonso at the FoCM website. And today, Afonso will talk about computation, statistics, and optimization of random functions. So let me stop sharing the screen and give the microphone to Afonso.
Hey, thanks so much, Agnes, for such a kind introduction. Thank you all for coming. It's my great pleasure and huge honor to be here and give this talk. Of course, I would have liked to see all of you in Vancouver, but hopefully, 2.5 years from now, we'll have the chance of all seeing each other there in the 2023 version of this talk. So I'll tell you a bit about an overview of some of my research interests and some of this area that I work on, both me and colleagues. So I'm going to tell you a lot about sort of a way in which mathematics tries to understand certain problems in data science. In particular, how computation and statistics and sort of understanding of how difficult or easy it is to optimize certain distributions of functions can tell us something about the difficulty of learning and of doing inference. So usually I start by sort of giving some numbers, or I used to start by giving some numbers of how much data there is these days and how much data gets collected and sort of how much potential is there in analyzing data. But I think, these days everyone is aware of this. So instead I'll treat you to a cartoon. So my slides aren't changing. So let me see if I can fix that. Okay. So I thought this was, cartoonist puts in pictures in a much clever way than we could ever put in words. So I'll just let you enjoy the cartoon for a second. Data is sort of everywhere these days, and there's incredible value in it. And so what I'm interested in understanding is really the mathematical side of this and the fundamental side of this, and core questions such as what are the limits to what we can learn? So what are the limits to what we can do with data? Which methods work and why? Like, why do certain methods work? Why some other methods don't? what are the bottlenecks? Are the bottlenecks about the quantity of data, the quality of data, or are the bottlenecks about the quality of our algorithms, or the quantity of computational power, or the quality of it? And maybe something that feels that's a bit less talked about, but I want to mention a bit in the end, is when can we a posteriori evaluate the quality of our learning or of our estimation, and maybe even produce certificates that, at least in certain notions of objective functions, we're actually giving the right answer, or at least an answer that's close to the right one. And so, of course, this question of what are the limits, what we can learn, what are the limits to statistical estimation, let's say, has been studied for centuries now. Okay, so let's go through a bit of history. So I did my homework, and this notion of not always you have enough data to learn very precisely is sort of already in the 1700s already present in the whole notions of Bayesian statistics, right? So when we have a posterior distribution for our parameter, right, already there is some notion of uncertainty. So already 300 years ago, there was a notion of, maybe more data can tell you more, right? This was made a lot more precise in the last century. Maybe, and I'm highlighting here a few important, discoveries or notions. One is definitely of Fisher information. So, right, Fisher information attempts to answer the question of how much information about a parameter of interest is there in a sample. Now, it's a very local notion of information, but nonetheless, it attempts to measure this. Then 30 years after that comes the Neyman-Pearson lemma and a lot of the theoretical understanding of the limits of hypothesis testing, right? Where instead of just estimating a parameter or learning something very complicated, we just want to distinguish two states of the world. Right? Am I in state A or state B? And I just want to be able to get and to understand how much data do I need and what quality does it have in order for me to be able to reliably tell if I'm in one state of the world or the other, to do hypothesis testing, say, from two simple hypotheses. Right, then a few years later, this got much better understood for statistical estimation with things like Kramer-Raubaum and so on. Right, then comes the 40s, and in the 40s, right, there is the birth of sort of information theory with a lot of the work of Shannon and Hamming and so on, which gives sort of less local notions of amount of information and measuring amount of information, right? Such as Shannon entropy and so on. And in the last, 70 years or so, a lot has been developed. And I give here a few examples, and of course, many people have been involved in this. But all of this is trying to answer the question of when is there enough information in the data? Right? When is it that there is really the data? There is enough data to solve the problem, to estimate the parameter we want, to solve the problem we want. Right? Measures amount of information in a way. Okay? However, as I'm sure when we want to actually learn or estimate, right, when we do statistical estimation or some form of learning, at the end of the day, almost always, we also do some form of optimization, right? So we get the data, and then we have some kind of model, and then we try to find a parameter or the signal or the model that best fits the data, right? So there's many classical examples, like if you do maximum likelihood estimation, you have to find the set of parameters that maximize the likelihood. Even in more modern tools, like if you train a neural network, at the end of the day, you are trying to optimize the parameters in a way that best fits the data. And so almost always, to learn from data, you also have to solve some kind of computational problem. And so a very natural question is, of course, not only if there's enough information in the data, but are these computational tasks actually feasible? Do we actually have enough computational power, or are algorithms good enough to actually solve these computational tasks? And we know now that, or we believe that there's problems that are difficult. They are inherently computationally difficult, right? And we know that they are, at least in a certain notion, difficult, this notion of NP hardness, right? And so there's some problems that we believe are difficult. And I use here the knapsack example because, so the knapsack problem is you have, right, the trunk of a car, you have many bags, you have to decide, do the bags fit in the car or not? And this problem is a good example because it's clear that solving this problem is difficult. If you've ever gone on vacation, you can probably relate to that. But if someone attempts a solution, it's very easy to check. You just close the trunk of the car. If it closes, the solution is good. And many problems of the type that we're talking about here of fitting and so on, measuring the fit to the data is usually not the issue. The issue is, or at least after you have a model, the issue is really finding the parameters that maximize this. So in a way, it's a natural note. Usually these problems tend to be NP hard. And this notion that finding a solution is difficult, verifying it tends to be easy. Now, if you go into the history of trying to understand the computational hardness and feasibility of computational tasks, right? So I did also my homework here, and there's this beautiful letter from the 50s that Gödel writes to von Neumann, essentially asking whether, something of the type, do you think there's actually problems where there's some fundamental reason that in order to solve them, we need more computational time than to read the input, basically, right? Which is the whole notion of computational hardness. The feeling I got was that Gödel was interested in understanding whether an algorithm could potentially prove mathematical theorems, right? Given Gödel's interest. And proving a mathematical theorem is very much the type of thing where finding the proof is much harder than checking it. Sometimes checking the proof is also difficult, but finding it certainly is a lot more difficult. And so Gödel was interested in understanding whether mathematicians could be replaced by machines, and essentially this, if you read this letter, at least was this impression I got, but it was clear that he already suspected that there were problems that were fundamentally difficult. And there's also a letter from John Nash from around the same point, more on the cryptography side of things, also asking whether there are basically codes that are hard to break in a certain sense. Okay? And it's kind of interesting, that these people were, right, some connections with Princeton, or a lot of them were in Princeton. So clearly this ideas must have been floating around in the 50s there. And this didn't become sort of to the maturity that we have now until the 70s, when the notion of NP hardness came along, and right, Cook and Karp and so on argue that we don't know if these problems are hard, but at least we have a huge class of them that if one is hard, then all of them is hard, or if one is easy, then all of them are easy. And so because we've all been trying for many, many years to solve essentially all of them, and we haven't succeeded any of them, then they're probably all difficult. But this, from the viewpoint of learning and statistical estimation, I think the natural question to ask ourselves here is, okay, so we come up with some model that now we want to fit. We want to learn the choice of model parameters that best fits the data in some model. Maybe sometimes we get a problem that's just too hard, our computer can't handle. Should we be designing statistical models in a way that makes optimization easy? Right? Should we be using the lessons that we learned from computational complexity in order to design statistical models that are easy? And I mean, this is one of the reasons why oftentimes one picks statistical models or learning models that have linearity and convexity and so on. It's not the only reason, but it's part of the reason, because they give rise usually to optimization problems that tend to be easy. Okay? But so let me contest that for a second. I mean, many of you are already thinking, right? Neural networks certainly don't satisfy these characteristics. But let me give you even much simpler examples that we can understand mathematically a lot more of a complete way. Okay, so here's an example quite close to heart. So the goal here is to do community detection. Okay, so just there is a graph on n nodes, and we want to split it into two communities in a way that the communities are very dense within and are very connected within and not connected across, right? But so we want to understand this problem mathematically quite well. So we're going to have a generative model for the data, right? In order to have sort of a completely specified model that then we can study. And so a very nice model for this is the stochastic block model. Okay, so I'm going to describe this random graph model right now. So I draw a graph on n nodes, okay? And then I separate it into n over 2 nodes on each side. So n over 2 nodes, n over 2 blue nodes, and n over 2 red nodes. Okay, so there's this side. These nodes get over here. These nodes get red over there. Okay, and then I'm going to, for every pair of nodes, I connect them with probability p if they're within the same community. So 2 blue nodes get connected with probability p. The same thing for 2 red nodes. And if they are in another community, they get connected with probability q that is smaller than p. Right? So here I should think of q as being smaller than p. Right? Okay. And so now if p is much bigger than q, clearly this graph has a very strong community structure. If q is the same as p, then it doesn't really. Okay? So now in order to formulate sort of a learning problem, an estimation problem, what I'm going to ask is I'm going to now jumble all this together. Okay, so the nodes get all together. I take away the colors. And now I ask, can we recover the colors or the partition, right? What is blue and what is red is sort of lost because there's a symmetry in this problem, but can we recover the partition? Right? And so, of course, what we would try to do is try to split the graph into two very strongly connected communities that are not quite as connected in between. So it's sort of clear what to try algorithmically, right? But it's not quite clear when it can be recovered, what algorithms work, and so on. So you sit down, try to do the math. First thing you realize that sort of the interesting regime is when the probabilities are scale like logarithmic log n over n. This is when the average degree becomes logarithmic, and this is when sort of you guarantee that the graph is connected. Okay? But the actual scaling is not so important. But you get you now set this p and q to be on this scale. So now it's alpha log n over n, beta log n over n, and you try to work out for which values of alpha and beta is it that you can recover this, right? So the bigger alpha is and the smaller beta is, the easier it is to recover the collars. And it turns out that one can show that if square root alpha minus square root beta is bigger than square root 2, right? So a very simple expression, right? Very, very simple expression. Then minimum bisection, which would be the natural algorithm. You just bisect the graph in a way, right? You find two equally sized communities in a way that it cuts the listings in between, that this coincides with the true communities. Okay? And essentially, this is an if and only if. So if you're below square root 2, then it's easy to show, it's possible and not so hard to show that this is essentially impossible to find the labels of the communities. Okay, so this is done with tools from information theory and the classical tools from statistics. But now you realize that, well, minimum bisection is actually one of the NP-hard problems, right? It's one of the problems that was said that if all the others are if any of the others are difficult, minimum bisection is also difficult. So we really believe that that minimum bisection is something that we cannot solve that there's no efficient algorithm that can solve minimum bisection for all graphs. Okay, so this is one of the situations where we have a theorem saying that it's possible to recover the true communities, but our algorithm is inefficient. We cannot run it on a large graph. However, it turns out that exactly at the point where recovery is possible, so when square root alpha minus square root beta is bigger than square root 2, then actually minimum bisection can be computed efficient. Right? So actually certain heuristics to compute minimum bisection can be proved that they will give you exactly the minimum bisection and exactly the right communities. Right? Somehow the problem is getting easier, not only statistically, but also computationally. Right? And this is, of course, feels like a very sort of a wonderful coincidence, right? Because the problem appeared to be hard, but actually it's easy when we want to solve it. And the natural question is to ask, okay, does this always happen? Right? Is it that computational hardness is actually not a problem? And I want to share an example that sort of motivates or illustrates that we believe this is not the case. We believe that there's instances in which this does not happen. So let me show you a very classical example known as the hidden click problem. Okay, so here it's a very similar random graph model. So I draw a graph, I connect every pair of nodes independently with probability a half, right? Things like uniform over all possible graphs. And on the other hand, I do something else in which I plant a k click. So what I mean is I pick k nodes at random, let's say 4, and then I connect every single pair, right? And if they're already connected, then of course I don't add a double edge, it just stays. Okay? And I pick the k nodes at random. Okay, and now I can ask questions of the type, when is it that I can recover, can I find the click? But it turns out an easier question to ask is even, when can I distinguish the hypothesis testing between a graph on the left and the graph on the right? When can I detect the click? Okay. So if we, sit down, try to, and first of all, I guess a natural thing to do would be to look at the largest click of each one of these graphs, right? Because we just added a big click, so probably we can see by if we look at the largest click, we can see a difference, and so we can work out what the size of the largest click is. So if k is sort of large, then the largest click on the left is 2 log n, right? To show that it's smaller or equal than 2 log n is a simple calculation. Okay, and on the right, for sure, the click is larger than k because this was the click that we added, right? So could be that somehow there's a bigger click, but certainly it's bigger or equal than k. And it's not so hard to show that if k is bigger than 2 log n, then it can't be bigger. And so this means that as long as k is bigger than 2 log n, certainly these graphs look very different, right? If I just compute the largest click, they're going to look very, very different. However, if you go look at algorithms, there's basically an algorithm from around over 20 years ago now that gives an efficient way of distinguishing these two graphs or finding the click, detecting, and so on. Basically, when k is bigger or equal than square root n. Okay. This is very different, of course, than the 2 log n bound at which the largest click becomes a very good statistical test, but of course is a computationally hard one. Okay. And sort of we believe as a community so much that this efficient algorithm can't be beat that it's even used as a reduction primitive. right? So already for almost 10 years now, Berthet and Rigolet used it to argue that a certain version of sparse PCA is difficult. I'll mention sparse PCA in a second. That if you had an efficient algorithm to solve sparse PCA, then you would have an efficient algorithm to beat the Alon Krivolevich-Sudakov algorithm, and we don't believe that is the case. Okay? So this gets used to sort of, show that other problems are hard, in the sense that if they were easy, then this problem would also be easy, and we really believe that this is hard. Okay, so this suggests sort of a hypothesis that I like to call the statistical computational gap hypothesis. That in these problems, there's a notion of signal to noise ratio. So I'm using here graph problems because they're much easier to show a picture of and to think about with a visual cue. But you can imagine this happening in problems involving matrices, as we'll see in a second, and imaging and so on. And so SNR sort of measures how easy my problem is. So here would be the size I click, I add. In the stochastic block model would be how big P is with respect to Q and so on. And it's clear that if the SNR is too small, then there's basically not enough signal. Right? So the problem then is impossible. Right, and then the traditional statistics and information theory tools and so on distinguish when is it that at some point you do have enough information in the data. If you count the amount of information, there is enough information in the data and the problem starts being possible. And so there is enough information. However, it seems that in some problems, there is a hard regime. So what I mean by this is all efficient algorithms seem to stop long before the statistical threshold, and they seem to stop all at another threshold, which I'm calling the computational threshold. Okay? So these would be now efficient algorithms, so efficient algorithms. Okay? And there is a region in between in which there is enough information in the data, but somehow there seems to be a fundamental reason of why it can't be accessed efficiently. And so you should view this, for example, for K, this would be the 2 log n versus the square root n. And so one thing I'm interested in is how do we understand what's going on in this hard region, and how do we understand where this threshold is? Because in reality, in practice, and then we were not going to be able to solve things in the hard region. So while this measures the amount of information, this really measures in practice what one can do. And so it's important to develop tools to understand where this threshold is, and to understand mathematically what's about the problem that puts it into this category. Okay. So let me tell you very overview a few ways in which one can argue that a problem like this is hard, right? So the traditional NP hardness doesn't say, right, minimum bisection, say, is always the same problem from the viewpoint of computational complexity, right? So it's just an NP hard problem always, but NP hardness doesn't say anything about being hard for all graphs, right? Just that for any algorithm, there is a graph on which it shouldn't work, an efficient algorithm. Okay, so there's many different heuristics. I'm going to focus on my overview, on 2 classes. So one class, I would call it sort of geometry of solutions. Okay, so I'll do this via an example. Let's put our minds in the stochastic block model. Okay, so since the model is completely characterized, I could say that I draw the labels in the beginning at random, split half and half, and then I can talk about the posterior distribution of my node callers, of my partition, given the actual graph that I see. Right? Whether the problem is possible or not is basically whether this posterior actually is informative, right? Actually has some information about the true callers. Whether the problem is easy or not seems to have to do with how complicated this random distribution is, how complex it is, or something about its geometry. Okay? And so it turns out people in statistical physics have been developing tools to understand sort of complexity and geometry of random distributions for a long time. And this can be leveraged quite effectively, I would say, or amazingly effectively, I would say. And you can see maybe here the connection by thinking that each node label, maybe it's a plus or minus 1, right? And so you can imagine around each label, there's a spin of plus or minus 1. The fact that you see an edge or not you can view it as some kind of interaction on the posterior distribution between these 2 spins. So if you think in the sense of statistical physics, you could imagine that each of these things is a particle. They have some kind of complicated joint distribution on their spins, right? Because they're near each other, or they interact physically with each other. This creates some kind of interaction between themselves. So now they have a complicated joint distribution. And whether say, geometry of the probability distribution over the spins over the plus or minus ones might tell you something about, say, magnetism of the material. Maybe if everything points up, then this should correspond to something that's magnetic, and so on and so forth. Okay, so this is a very, very hand-wavy sort of explanation of where this connection is coming from. But it can make very, very accurate predictions about computational hardness of problems, not only in graphs, but also matrix recovery and so on. And this is sort of what fascinated me to start looking into this thing. And another, which I'm going to talk a bit about more today, I'm going to focus more in the second one, is you can focus on classes of algorithms, right? I say, well, I want to look only at local algorithms, or I want to look only at algorithms that are allowed to do certain things. And then maybe I can argue that because those algorithms only see part of the information, then I can maybe use the tools from before to say, well, that part of the information is not enough to give me what I want. Okay. And so one particularly fruitful technique is to restrict to low degree polynomials of the data. Okay. So I'll talk a bit more about this. So the intuition for this comes from sort of the sum of squares hierarchy in the theoretical computer science community, and this was made explicit in a very, very nice paper of Hopkins and Stoyer that I'll talk a little bit about. Again, there's many other heuristics, and I'll talk a bit about it in the end. I mean, one of the goals is, of mathematics here is to try to connect these different heuristics and so on. And in the end, I might say a few words about this. So now I'm going to talk about sort of give a few examples of problems. And in this part, this is the bulk of this is joint work with two amazing students in the postdoc at NYU. So I want to tell you about what is called the low degree method. So this answers the question in a way of what can we do if we are restricted to using only low degree information of the data, and I'll make all of this precise. Okay? So this is really suited for this sort of hypothesis testing version of the problem in which there's only two possible states of the world, either the graph has a clique or not. Okay? And in the community detection problem, you can also think of the problem where, well, maybe I don't have a community structure at all. The probability is just the same everywhere or not. Okay? And then this is one way to attack that problem, and it will give you very, very accurate predictions as well. Okay, so let me think now and let me explain this in general terms. So the goal is to do hypothesis testing between two distributions with error going to zero. Okay? Turns out that error going to zero is sort of the important, is the right thing to look at if what you want to understand is when you can recover the object or not. Okay, I won't explain why, but I can if there's questions in the end. Then you have two possible states of the world, usually a null model where there's just noise. Okay, so here you should think maybe, for example, the graph without a clique. Or there is what we call a planted model in which there is a signal. Here you should think of the graph without any planted clique, with the graph and then with a planted clique added. Okay, so the null model would be just the Erdős-Rényi graph without any planted clique. The planted model will be the one with the planted clique, but as we'll see examples of these problems with matrices, for example. Okay, and the goal now is to do hypothesis testing between these two possibilities. Either you drew a sample from something with no signal whatsoever, or from something with signal. Either you drew a graph without a clique or a graph with a clique. And the intuition you should have, or I mean, one can argue this a bit more precisely, is that if you're not able to distinguish between these two distributions, then you should not be able to find the clique, right? If you cannot even tell that it's there or that the signal is there, then you should definitely not be able to detect the signal. Okay? So the key idea is to ask ourselves, rather than putting ourselves in sort of the Neiman-Pearson framework, is to say, what if instead of asking, is there a statistical test that has sort of low error or something like this, we ask, is there a low degree polynomial that is big under the planted model and close to zero under the null model? Okay. And the idea is that, is to think of computing a certain notion of big and a certain notion of close to zero. Okay, so the idea is to maximize overall polynomials of degree up to D of the data, right? And maximize its expectation under the planted model while keeping the variance under the null model controlled. Okay, so think of it as maximizing the mean under the planted model while keeping the fluctuations in the null model controlled. Particularly if you can do this with a quantity that's going to infinity, it should mean that you're able to actually distinguish, right? Because the scaling of this polynomial in these two models is different, so you can use it as statistical test. Okay, so let's do some calculation. This is my only slide of math, I think. Okay, so what we want is to compute this quantity, and the nice thing is that this quantity can actually be computed in many cases. Okay, so the idea, the insight is just realize that we should change the variables so that everything is under these expectations under the null model, right? And when we do the change of variables, what we need to multiply on that first term over here, right, is just the so-called likelihood ratio, right? Is exactly the change of variables. Okay? But now that we have two expectations in their Q, this is now a very linear algebra problem. It's like an inner product and the norm, right? And so if we just define this inner product, like the L2 inner product in their Q, where it's just the expectation of the product of the functions, right? And the norm being the way that it's defined normally, then all this is here is the maximizing under a certain subspace, the polynomials of degree up to D, the inner product of L with F, right? Our variable divided by the L2 norm of F. Okay? But this we know how to do, right? The maximizer of this is of course just a projection of L on the polynomials of degree smaller or equal than D. Okay, so we define this object, the truncated likelihood ratio, right? The likelihood ratio again, it's just this change of variables over here, right? And we define L truncated to D to be the projection of L onto degree D into the polynomials of degree smaller or equal than D. Okay, and now of course the value of this program here is just the L2 norm of this object. Okay? So it's just the norm of the low degree likelihood ratio, and this is why we call this the low degree method. And as I have it here in small, as a comment for experts in these things in statistics, you probably will see the connections with Lecomte contiguity. So I'll just say that. Okay? And so now, right, we have this we can compute this quantity at least with respect to, right, as a function of this truncated likelihood ratio. And the idea heuristically is that if this quantity is going to infinity, then the degree D polynomial should be able to distinguish Q from P, right? Because if this quantity is going to infinity, it means that there is a polynomial that is the scale of the mean under P is much bigger than the scale of the standard deviation under Q, right? And so you should be able to distinguish because they get, right, the typical value under P and the typical value under Q get very, very far. Okay? This can be made all more precise, but I don't have time to do it here. And if this quantity is constant, it's bounded by a constant, it's O of 1, then the degree D polynomial should fail, right? Because then the difference between the means, the mean and then the Plankton model starts being of the size of the fluctuations. And so you are likely to make a mistake with positive probability and not get an error that goes to 0 and then goes to infinity. Okay, so this is the heuristic, is you compute this quantity, if it goes to infinity, you can distinguish with low degree polynomials. If it stays bounded, you can't. And to give you sort of well, not really a precise conjecture, but a conjecture that's formulated here in a sort of informal way, right? That shows up in Sam Hopkins' thesis from a couple of years back. For nice, and the informal part is the nice, but for nice distributions P and Q, of which all the ones I'm going to talk about are nice, then if this is bounded for a degree that grows bigger than log n, okay, so log n turns out to be the right degree to look at, then no polynomial time algorithm should be able to distinguish Q and P with success probability going to 1. Okay, so this makes a statement about computational hardness of hypothesis testing, right? And if you're aware with Lecomte contiguity, if you take D to be infinity, this is essentially Lecomte contiguity. I mean, not quite. And if there's any questions, I can talk a bit about it. Okay. But this gives you a way of measuring the computational complexity of hypothesis testing and arguing that a problem may be difficult, even though it's possible. And the intuition is that, there can be a more precise intuition maybe, or more general intuition, that somehow degree D polynomials in this context, they represent algorithms that take time n to the D. Okay? Not really n to the D, is n to the D with some extra logarithmic factors, right? But in a way, degree D polynomials are playing the role of n to the D algorithms, right? These logarithmic factors come from the fact that if you take, say, the leading eigenvalue of a matrix, this feels more like a logarithmic log n degree polynomial, but it's something you can compute in polynomial time, and this is where the log discrepancy sort of comes from. So very, very brief comment on that. And so you can make this sort of precise in certain ways. So one can argue that if this is actually bounded, if this likelihood ratio is bounded, then no spectral method can distinguish from P and Q in a certain sense. And we have reasons to believe that spectral methods are as powerful as at least the sum of squares hierarchy for average case problems. And we have reasons to believe that sum of squares hierarchy appears to, at least to some extent, to represent hardness in average case problems, at least for some problems, or at least with respect to algorithms we know. And so you can put some theoretical footing in this sort of meta conjecture, or this conjecture, and maybe I can talk a bit about this in the end if there's questions. But gives us a way of arguing about computational hardness, right? That's the key thing. Okay. So let me give you an example to convince you that this is actually something one can compute. Okay, and it's the first time I do this, but I'm going to use the fact that the talk is recorded to flash some math, and that you can pause in the recording if you want to see the sketch of the proof. But turns out that a very nice model is this additive Gaussian noise model. It captures more things than it looks when you just look at it. But the idea is that in one hand, you have some distribution that's equal to some signal that is also random from some prior plus Gaussian noise. In the other one, you have only Gaussian noise. Okay? And turns out that this likelihood ratio is quite nice to compute in this case. Okay, so I'll flash the proof. If you're interested in the proof, just pause in the recording and you'll see it. The sketch is here. Okay? But what I want you to focus in the talk is the fact that actually the square of this norm of the likelihood ratio is equal to something that's a very nice expression. So what you do is you draw two independent copies of the signal of X, and now you look at some truncated moment generating function of their inner product. Right? In the language of statistical physics, you draw two replicas and you look at some function of the so-called overlap. Okay? But now it turns out that this is something one can compute, right? And so if you think of D being infinity, and then degree infinity polynomials should sort of capture everything, then you would look at, right, the expected value of two copies of the exponential of the overlap, and whether then the problem is easy or hard, so you make D get smaller and smaller, seems to have something to do with the concentration of their overlap, right? It becomes a function of their overlap and something you can compute, right? So I want you to take from this is that this is something actually a beautiful formula that we can compute. I should say what I mean by the truncated exponential is you literally take the Taylor series and truncate at degree D. Okay? It's sort of amazing that the truncation in the data corresponds to the truncation in the overlap, but this is sort of it's some orthogonal polynomial magic that makes that be the same. Okay, so let's give a non-graph example. Let's talk about some matrices. Okay, so a model I really like is the Wigner spike model. So here I'm trying to learn some signal, a rank 1 matrix, from drowned in Gaussian noise. So the idea is that I have some vector V, like V is my signal, okay? And I'm trying to learn V, or detect V, recover V from VV transpose plus Gaussian noise, right? And lambda measures my signal to noise ratio. Okay? And if this is understood from the viewpoint of random matrix theory, and we know that if lambda is bigger than 1, this is the so-called the celebrated BBP phase transition, that if lambda is bigger than 1, then the fact that you added this rank 1 matrix will make one eigenvalue pop out of the supports of the Wigner semicircular law, of the Wigner random matrix. And if lambda is smaller than 1, then this eigenvalue starts being drowned in the support. And it's not so hard to show that, or at least with current techniques, it's not so hard to show that if lambda is smaller than 1, then, and this eigenvalue is inside of the support, is actually impossible to recover V or detect it with probability going to detect it successfully with probability going to 1. Okay. So for those of you that are more sort of statistically minded, you might be more familiar with the Wishart spike model, where you talk about covariance matrices. I'm using the Wigner because it's a bit simpler, but actually everything I'm going to talk about works just for the Wishart model, just the same. Okay. So now, so the story for the Wigner matrices is sort of, right, it's kind of clear in the sense that you either have enough signal to come out of the support or you don't, and you're done. But the computational interesting questions start arising if you put structure. So what if I tell you that the vector V is now sparse? So in particular, the vector V has rho n sparsity. Okay? So where rho is something smaller than 1. right? And now we can ask, can we detect it below this spectral threshold? Okay, so for the rest of this, think of lambda as like 0.99, right? You're shy of the spectral threshold, so you cannot do it just by the spectrum. And we ask, can we do it by exploiting sparsity? And so I'm interested here in giving lower bound. So the easier the problem is, the harder it is to give lower bound. So I even say that V not only is sparse, but it's drawn uniform from just either zeros or plus or minus 1 over the normalization to make it norm 1. Okay? And now if you ask, okay, when can you do this? If you work out what the maximum likelihood estimation gives you, you see that already for constant rho, small constant, it works. However, the computational cost, it basically amounts to checking every possible sparse vector. So, it's exponential for constant rho. And efficient algorithms exist essentially for when sparsity is square root n. Okay? And there is evidence that there's a real computational gap here, that you can't improve over this square root n, some of which based on reductions that I mentioned in the beginning from the planted clique, from the hidden clique problem. Okay. And so what I want to show you here is what can we do with the low degree method. Okay? So turns out that this is, right, it's not hard to see here that this is a version of the Gaussian additive model. Okay, so we can do hypothesis testing between either we actually add the signal from the sparse prior or we don't. And now we work out what the likelihood ratio is, and you can show that for lambda constant smaller than 1, then if the degree is smaller than rho square n, then polynomials of that degree shouldn't work. And if the degree is bigger than rho square n, then they should work. So immediately what this tells you is makes you conjecture that if you're below this place where the spectrum tells you something, where you really have to exploit the sparsity, then exploiting sparsity requires exponential rho square n computation. And this is not the same, so it's a precise sub-exponential requirement, but it's not the same as going over all sparse vectors. So it's actually not obvious that an algorithm exists, but once you know to look for one, indeed one exists, and actually there is another one in the literature exactly with this runtime. Okay, so of course, sub-exponential is still something you wouldn't be able to do in practice. But the interesting thing is that this is sort of not a trivial computational complexity, because it doesn't correspond to looking over all sparse vectors. That would be rho n. This is an improvement over that. However, the best algorithms known match this, and no algorithm can beat it, right? So this, to me, gives me more confidence that probably this conjecture actually is getting at something, right? It's potentially this statement is falsifiable in the sense that we're making very precise conjectures about the computational hardness needed to exploit sparsity in a very popular problem. Okay? So now in the last 5 minutes, I want to tell you a little bit about what all this construct of hardness of hypothesis testing can say about problems that are not so statistical. It's really about optimization. So we're going to be in the same object, but switch gears just a little, and this will be a brief detour. Let's look at the problem of computing the ground state of the SK Hamiltonian. Okay, if you don't know what this is, it does not matter. It's just you take W of Wigner matrix, so Gaussian entries with variance 1 over n, and I define SK of W to be the maximum over the normalized hypercube of the quadratic form XTWX, right? So I take a random quadratic program. Right? Now, let's look at the value of this quadratic program. Well, maximizing over the hypercube is for sure smaller or equal than if I was to maximize over all vectors with L2 norm 1. And that would be just computing the leading eigenvalue of the matrix. So for sure, the maximum is somewhere below 2, because I know that the leading eigenvalue of the Wigner matrix is 2 with high probability. And turns out this is something important in statistical physics. People have computed it. It's around 1.5. It's so-called the Parisi constant, or twice the Parisi constant. And now you can ask, from a viewpoint of how difficult optimization of this is, of a random quadratic program, how well can we approximate it? Can we find solutions that get close to this with high probability? Amazingly, we can. So there's been improvement over time, but now due to work of Andrea Montanari, we believe that there is an algorithm based on message passing that we believe gets arbitrarily close to the right answer. Okay? It's conditioned on a certain conjecture that I don't have time to talk about, but we strongly believe that this reaches the point. Now, the really interesting thing is that does not seem to be a better upper bound. Okay? So if I give you the following game, that I give you a matrix W, and instead of finding a solution, what you're trying to do is giving an upper bound on this quantity. Right? Think in terms of duality, say. If I give you a matrix W, you have to find an upper bound on this quantity. So you come up with some function, right, f of W, and I want that f of W is always bigger or equal than sk of W. Okay? And now I evaluate how good f of w needs to be efficiently computable. And I ask you, how good is f of w for Wigner matrices typically? What's the expected value of f of w under the Wigner measure and the Gaussian measure? Okay, so it turns out we cannot, it doesn't seem like, seems like we can't do anything better than 2, right? So the largest eigenvalue of w would be such a function. It gives 2. If you go on the sum of squares hierarchy, we now understand that it basically doesn't seem like we can get out of 2. And what I'm going to tell you about is a different kind of evidence that indeed, I'm going to give you an argument that indeed we really don't expect to be able to improve over this. That there's a fundamental hardness in being able to certify an upper bound better than 2 for the ground state of the Cherenkov-Kirkpatrick Hamiltonian. Okay? So I'll just briefly mention how this argument goes without actually showing any of the details. But the idea is this idea of quiet planting. So what we do is we construct a distribution over matrices, W prime, a new random variable, like a tampered distribution, let's call it a quiet planting, such that 2 things happen. One, the typical value of this SK for W prime is 2. And secondly, we can use the machinery from before to argue that distinguishing from this new random variable in the Wigner matrix is computationally hard. So we're hiding a much bigger value of SK, but we believe that this is difficult to distinguish. Okay? Statistically speaking, probability, distance between measures, and so on, these 2 distributions are completely different, right? If you compute SK of W, it's a completely different probability distribution for both. The probability that the Wigner has an SK of W close to 2 is extremely small, right? And so here, how we construct this distribution, I don't have time to explain, but basically you need to understand something about the spectrum and plant it somewhere on the spectrum and then use the machinery that I showed below. I'm happy to talk more about it offline too. Okay? But the point is that you can make an argument, using statistics, you can make an argument about hardness of optimization. And not only in matrices, for graphs, you can also do this. So in particular, for example, here a problem in graph theory that we've done this for is if together with also Jess at Berkeley and Chris in Santa Fe, is if I take the uniform distribution over D regular graphs on n nodes, and I ask about its chromatic number, right? So chromatic number is how many colors do I need so that I can color every single node in a way that not any 2 connected nodes by an edge don't have the same color. Okay, so you work out the math and you see that the chromatic number for this is D over 2 log D. But now I can ask the question, okay, so what if finding the chromatic number is hard? So I can ask, okay, so what if I want to actually color it efficiently or give a lower bound on the number of colors? Argue, no, with the value K, there is no, I can give a certificate that there's no, for a particular graph, that there's no coloring with that number of colors. Okay, so it turns out that this can be adapted. And I should maybe say that the intuition on the spectral planting in the matrices is actually key here. The planting that's done here is sort of spectral in a way. I don't have much time to describe it, but it really uses insight from the matrices. And it can be adapted to show hardness of certifying non-colorability below much lower level of half square D. So just to show you the picture of what appears to be going on here is searching for a color seems to start being hard. Searching for a coloring seems to start being hard when I give you less than D over log D colors. The true coloring number is D over 2 log D. If you try to plant with ideas similar to the stochastic block model, you can do quiet planting up to root D. And if you use the sort of spectral intuition obtained from the matrices, then you can come up with a more quiet model, a better way of hiding a coloring, which we call equitable stochastic block model, and had this name from physics, that can get you to square root D. And this is exactly the so-called Hoffman bound. So there is an efficient algorithm to certify here, and sort of conditional on all these conjectures sort of resolves the hardness of certification in this problem. Okay. And yeah, so sorry for taking 1 or 2 minutes too long. And yeah, I'm very happy to answer questions. Again, it was a pleasure and it's an honor to give this talk. And I hope to see all of you in 2023 in the conference.
Thank you very much. So I sent a message out. You can ask questions either by typing into the question and answer button, or I think you can also raise your hand and we could hear you. So I don't see yet any questions, so please type in if you have any questions. We will wait a little bit. Let me ask a question while we are waiting for the other one. So you mentioned, my interest is in the sum of squares, and you mentioned it several times and mentioned the spectral methods. That can you talk a little bit more about that, just briefly?
Yeah, so on why, yeah, okay, it's a delicate thing here. So, okay, yeah, let me say a few more words. So you mean,
yeah.
Okay, so there's two statements here.
Mm-hmm.
The first statement is, I would say, less surprising, and the second statement is more spectacular, I think. So the first statement is just basically that a spectral method is a bit like a low degree polynomial, right? Because you can compute the leading eigenvalue by the power method, and so it looks very much like a polynomial of the entries of the matrix in a certain sense. That's sort of the key behind this. Now, the second one is sort of much more spectacular. So this comes from the theoretical computer science community. And what they showed is that, for a lot of these average case problems, if sum of squares works, then modulo, I mean, there's a certain conjecture in there, but a very believable conjecture nonetheless. But they argue very strongly and with mathematical statements that if you have a sum of squares algorithm to solve one of these problems, then there is also a spectral method that works. That would be much cheaper to implement. So the algorithm, okay, I don't know if I should try to, in a few words, describe the algorithm. It really is a tour de force what they do. But the way I see it is, if right, so if there's this powerful tool from theoretical computer science, from the sum of squares community, which is called pseudo calibration. So the idea is that you can argue that sum of squares doesn't work for an average case problem by showing that, for finding a certain structure, by showing that even when the structure isn't there, you can construct a sum of square solution that thinks the structure is there. They call this pseudo calibration. So you find a set of pseudo moments in this sense that make it look like they found a solution, but they're actually completely feasible even when the structure wasn't there to start with. So this is known as pseudo calibration. And so if sum of squares works, then pseudo calibration shouldn't work, right? Because otherwise you'd be proving that sum of squares doesn't work, and it does work. And they have this really nice idea that if pseudo calibration doesn't work, then pseudo calibration is some form of like infinite dimensional convex program in a certain sense. So if it doesn't work, there must be some kind of dual that must be large. So there must be some kind of dual certificate of why you can pseudo calibrate in sort of this infinite dimensional space. And turns out that this dual is a spectral method. Okay, I don't know if I'm making justice to their work, but in a very high level, this is what they do. They show that if you can't, if you cannot pseudo calibrate, then there must be a spectral algorithm that doesn't let you, and therefore there must be a spectral algorithm that recovers the structure whenever sum of squares does. I mean, it's really a beautiful argument that they have. Yeah.
Thank you. So we have a question now in the question of answers. Can you read it? I will read it out. What is a simple example of a method captured by low degree polynomials?
So spectral method would be the simplest instance. But usually any iterative method that involves some type of, right? So if I have a low degree, if I iterate a polynomial just a finite number of times, then this is still low degree in the sense of the degree being smaller than log n. But usually we're trying to capture low degree spectral methods. So there's a very large class of methods for many of these problems in which by spectral method, maybe I should be a bit more precise. What I mean is you build a matrix on which the entries of the matrix are data dependent. They're usually polynomials of the data, low degree polynomials. Oftentimes they're just data points. And then you compute the leading eigenvalue of this matrix, right? Think something like principal component analysis. In the sparse PCA, it would make sense that you look at the leading eigenvalue. And so these are low degree algorithms. But actually, most class of algorithms that we know, they in a certain sense, they're well approximated by low degree polynomials. Right. Maybe I should say that, yeah, maybe let me just add that really what's important here appears to be not the degree, like, if the function that you're using or the algorithm depends in one variable in a very high degree way, this is not really important, and probably these things are still okay. In fact, the original conjecture of Hopkins talks about degree in the sense of each term, how many variables it has. It really is measuring interaction by how many variables are in each term, not so much at the degree on each term, on each variable, sorry.
Here we have another question by Peter Bergiser. How does the evidence for computational gap relate exactly to computational complexity theory? It will be rather on some kind of average complexity, right?
Yeah, for sure, for sure. There's for sure it's some form of average complexity in the language of computational complexity. Now, the problem with average complexity is you need to have a measure of the distribution of the input in which you take the averages. And here the averages are taken sort of in probability distributions that are motivated by problems in inference and learning. But yeah, it's definitely average complexity. But there's very few examples of where you can use traditional computational complexity like NP hardness to argue average complexity. There's this beautiful example with the permanent that you can argue the permanent of a random matrix is just as hard as compute as the permanent of the matrix in the worst case. There's that beautiful argument, but I don't know many other that can reductions of this type, which is unfortunate. We should definitely have more, but it's hard because it's so distribution dependent that seems very difficult.
Well, thank you again for Afonso. If there are any more questions, you can still type them in, and Afonso can type the answer as well, right, Afonso? So
for sure, yeah, it'd be my pleasure.
Yeah, so keep asking questions, and thank you again for the speaker. And now we will continue with our second talk, and I would like to introduce our second speaker, Caroline Uhler. Caroline received her PhD in statistics from UC Berkeley in 2011, and presently she is the Henry L. and Grace Doherty Associate Professor in Electrical Engineering and Computer Science at MIT. She's an elected member of the International Statistical Institute, a recipient of the Simons Investigator Award, a Sloan Research Fellow, received an NSF Carrier Award, a Sofia Kovalenskaya Award from the Humboldt Foundation, and a START Award from the Austrian Science of Foundations. Her research focuses on statistics, machine learning, and computational biology. Today, she will talk about and you can read the title, Causal Inference and Overparameterized Autoencoders in the Light of Drug Repurposing for COVID-19.
Thank you very much, Agnes, for this kind introduction, and to everyone for inviting me to speak here. I think it's a wonderful idea of putting this together as a virtual seminar series, so thank you very much to all the organizers, and I'm really excited about the talks to come. So I decided to shorten the talk a little bit, the talk title a little bit. So I'll talk about causality and autoencoders, and in particular in the light of drug repurposing for COVID-19. So the group's research over recent years has really been focusing on, how can you learn causal relationships among variables from data? And we've really come to appreciate how this problem really requires insights from many different areas in mathematics. And so I'm going to tell you a little bit about that today. And now, due to the current crisis, we have, in fact, in recent months, mainly been working on research related to COVID-19, and in particular, related to the problem of how to identify drugs against COVID-19. And we found that, these methods that we have been developing for causal inference are really critical for actually identifying drugs against COVID-19. And so that's what I want to talk about today. And in particular, highlight, the kinds of math that really went into achieving these kinds of new methods, or this new computational platform for the identification of drugs. And so what I want to do is just start off with a slide which tells you a little bit about how does drug development work, and what are the difficulties in COVID-19. Now, as I'm sure all of you know, is that the process of developing new drugs is, very, very long, right? It has to go through many trials, and most of these drugs, in fact, fail. So given the urgency of this particular situation here, where so many people are dying, there is really only one viable approach for identifying drugs. It's known as drug repurposing. So you have, a whole lot of drugs that have already gone through trials and that are FDA approved for particular diseases. And now it is actually much faster to try to identify some of these drugs that could maybe also be effective in a very different disease context, namely SARS-CoV-2 or COVID-19, because these kinds of drugs don't have to go through the safety and dosing trials anymore. So you can directly go to the trials where you actually test whether this particular drug is also effective in the setting of COVID-19. So that's what we want to focus on here. So this problem of drug repurposing. Okay, so we're only looking at drugs that are already approved. And among these, we would like to identify drugs that might also be effective against COVID-19. Now, how do drugs in general work? So in general, a drug is supposed to target a particular protein. And by targeting it, it usually, there are also other drugs, but it usually makes it dysfunctional, so that this particular protein cannot play its role that it is usually supposed to do in the downstream tasks. Okay, so what are proteins that you want to target? Well, these are proteins that usually regulate genes that are now dysregulated by the disease. Okay, so you'd like to find these, very central proteins, central in terms of the disease network. So, think of a network like this. Of course, it's a large network. It has like 20,000 nodes. We have 20,000 genes in humans. And you have some genes here that you can measure, that you see they are dysregulated by the disease. And so good drug targets are ones that are somehow central, that are connected to many of these genes that are dysregulated by the disease, because the hope is that then, these might actually change the effect of these genes and maybe even be able to push the expression of these genes back to the normal state. Okay, so that's kind of how what the kinds of drugs or what the proteins or the targets are of drugs that you want to identify. Now, in general, drug discovery is still, mostly a very experimental process, but, more and more computational methods are being developed. And in fact, some computational methods have also already led to successful drugs. So what are these computational methods that are being used? And in particular, what is the data sets that you can use in order to identify drugs in this way? So one of the data sets, and I'm going to actually present it later in the talk, is our very large scale drug screens. So here you would have many, many different drugs or even molecules or even, knockout experiments. So all kinds of different perturbations that are applied to different cells. Okay, and what you get to measure in this particular drug screen that I'm going to show is a 1,000 dimensional vector, which measures, how the expression of the genes in these cells. Okay, so you have a drug applied to it and you apply to a cell and you get to measure what is the effect of this drug. And so this is what you would call a drug signature, is just, you get to see how the cells look like before the drug and after the drug. And so this vector in this 1,000 dimensional space, which goes from the mean before the drug to the mean after the drug, is called the drug signature. And you can do the same for diseased state, right? I have cells and I can measure how they look like before, without the disease, and with the disease. And that gives me the disease signature. And now the most popular approach is just to choose the drugs that are the most anti-correlated, so where the drug signature is the most anti-correlated with the disease signature, hoping that then the drug will push back the effect of the disease back to the normal state. Okay. Now, what is the problem with this approach and why does it usually not work? Well, so if you're thinking about it in these big, big drug screens, the human body has many different cell types. So in these big drug screens, you usually have some particular cell lines that have been used. Often these are actually cancer cell lines. And so on these cancer cell lines, in this particular one, there are about 70 of them, you have all these drugs that have been applied to it. Okay. But now we want to say, for COVID-19, we want to say something about lung cells, right? These lung epithelial cells are the ones we care about. Those are the ones that are, at least at the beginning, most affected by SARS-CoV-2. So the problem is that drugs have different effects on different cell types. So they will have a different effect on neuron cells as they have on, epithelial cells as they will have on any other cell type. So, and, we cannot, or these drug screens can just not be applied to all different cell types that we have in our body. So then the question is, from these drug screens, where you do know the effect on certain cell types, can you now tell from this data, can you now predict what is the effect of these drugs on a different cell type, on one that has not been measured before? So how can you get drug signatures that generalize across different cell types? So that's one of the problems I want to talk about today. And you'll see that actually quite nice mathematics comes into this particular problem. So that's one approach to actually identifying drugs for particular diseases. A different approach is based on networks, and that's another approach that I'm going to talk about today and also show you the math that comes in. So the other kind of data that is really widely available are these protein-protein interaction networks. So these are these large networks where the nodes are proteins. You can map them back to genes. And what you see is, which protein can interact with which other protein. So it's a very large undirected network, which is usually actually cell type agnostic. Okay, so it doesn't usually differentiate between different cell types, just not known how it is in different cell types. And now these approaches that use these protein-protein interaction networks, they go based on, what I kind of described before. So you want to actually target a protein that is kind of central based on all of the genes around that have been changed by the disease. Now, I already put these two pictures here. So these protein-protein interaction networks are usually undirected. Now, but the true graph is a directed graph, right? Genes regulate each other. So there is an underlying true directed graph of how regulation happens in these cells. Now, if the true graph looks something like this, then this target in here, this protein target, is certainly not a good drug target, right? Because if you target this fellow here, nothing is changing, right? Because all of these genes have a causal effect pointing into this target here. So this would be a very bad drug target, although it is very close to all of these genes that are differentially expressed or changed by the disease. However, if the true graph looks something like this over here, right, where you have a protein in the middle that has an effect on all of these other genes that are actually changed by the disease, well, then this might be a good target if it has the right effect, right? At least it has the chance of affecting these genes that are changed by the disease, and maybe it could actually get them back to the normal state. So you see how important it is that we actually learn the directions of these regulatory relationships, right? We really need to know the directions, because a drug, is an intervention in the system. It can only have effects downstream. It cannot have effects upstream. So really what we need to do here is to actually be able to learn this causal graph. And so those are the two causal problems that I want to talk about. And I'll first start with the problem of learning causal graphs. And here I think, there is something that is very different in this problem in biology than it is in other scientific areas or social sciences, etc., is that in biology, you have interventional data, large-scale data. So we have drug screens. We do have other interventions like these, CRISPR knockouts, where you just go in and, you can actually change. You can just set the expression of a particular gene to 0, right? And see how the expression changes of everything else. So these interventions should be very, very powerful to learn causal relationships, right? Because an intervention only has an effect downstream. Well, if I intervene something and I know that some node is changing, well, I know it is downstream. So that should help me to actually learn these directed structures or these causal structures. And so what we did here, and so obviously, because this data is only becoming available in biology and not anywhere else, there's really not much in terms of theory of how to integrate observational and interventional data to be able to learn causal structure. And so what we needed to do, and what we have done over recent years, is to really build a theoretical and algorithmic framework for learning causal networks from such a mix of observational and interventional data. And so that's what I'm talking about here, how to learn these causal structures when you have both data. And then the second problem is the one that I mentioned before, where now you have drugs, interventions applied in one environment, say in one cell type, But now I really want to predict, well, what does this intervention do in a different cell type? So here I have a red cell type. Here I have the same interventions. You see, it's the same drug. It has the effect on the same nodes. But now I want to know, what does this intervention, this particular drug, do when I apply it in a different setting on a different cell type? So this generalizability of these drug or perturbation effects is what I'm going to talk about next. And then putting both of these things together in the setting of COVID-19, kind of to solve the problems that I described before. Okay, so I'll start off with this problem of learning causal graphs. And obviously, you know, causality is something that has kept humans busy for a long time. It is, of course, a very important problem in science in general. And so this has a long history. And in particular, the framework that I'm going to be talking about is one that was introduced by Sewell Wright in the 1920s. Then came quite a long time where not much happened in causality. It was actually doubted that some of this work was right, but it took quite a long time until, you know, people really recognized how important this work was. And then people built, in particular, there were like contributions from 4 main researchers who really built the foundations of causality. And that's Julia Pearl, Jamie Robbins, Don Rubin, and Peter Spertus. And I also want to show just how interdisciplinary this area is. So Sewell Wright, he actually built the first foundations. He came out of biology, so he wanted to study heredity. So he looked at, you know, heredity in animals. And that, of course, is a causal process. And so you want to represent it with these directed graphs. And that's how he started thinking about it via these directed graphs. And then these people are actually all from very different areas. So Julia Pearl comes from theoretical computer science, Jamie Robbins from epidemiology, Don Rubin from statistics, and Peter Spertus from philosophy. And so it was really important that all these different kinds of ways of thinking came all together to build the foundations of causality, which is, you know, what we're going to use here today. So I will just tell you the basic framework, which is the one that was already set up by Sewell Wright, namely that, first of all, the causal relationships will be represented by a directed acyclic graph. So that's a directed graph with no directed cycles. Now, why does this make sense for causality? Well, causality can only have an effect forward in time. So you can never get back. Okay, so that's why you'll never have a directed cycle. Also think of heredity, right? How it was introduced by Sewell Wright. It's always a directed acyclic graph. And now in terms of what this directed acyclic graph represents, well, every node, now think of genes, for example, and the edges correspond to gene regulation. So every node is associated with a random variable, okay, as you see here. And the random variable is just a function of its parents. It's a very intuitive model. It's just a function of its parents and some noise. Okay, so if we look at this, so x3 here, you see, has no parents. So x3 is just some function of noise. Then x1 here has only one parent. So x1 is a function of x3, its parent and noise. And for example, here x4 has 2 parents. So x4 is a function of x2 and x3 and some noise. And, you know, the only assumptions, I mean, we're not making any assumptions on these functions. They can be nonlinear. They can be linear if you want to make it somehow easier. And we are also not making assumptions on the noise. These noise terms, all they have to be is independent of each other. Of course, they can be Gaussian if you want to make it easier, but they're in general not Gaussian. Okay. So this is the model. And so this model now defines a joint distribution over the nodes. Okay. Now, what is interesting, and that's the standard kind of Bayesian network if you're familiar with Bayesian networks, and otherwise it doesn't matter. So this defines an observational distribution. But now comes maybe the more interesting part for causality and if you're starting to think about interventions. So this model, in fact, also defines interventional distributions. And now I'll define what interventions are. And here I'm using this language that was introduced by Julia Pearl, this do intervention language. Okay, so what is an intervention? So an intervention is, think of a knockout experiment as maybe the easiest. I'm going in and I'm taking a gene and I'm just setting it to 0. Okay, because I'm actually cutting it out. So I'm setting it to 0. So what does that mean? So this is how it is represented. It's represented as do x2 equal to c. So it's really an assignment. So I'm assigning to x2 the value 0. Okay, I'm changing this assignment here. I'm setting it to 0. Well, what does that mean if you look at this particular network? Well, it means since x1 is upstream of x2, nothing changes to x1, right? x1 is still a function of x3, and x3 is still noise. However, downstream things change because x4 is a function of x2. x2 was changed, so x4 changes. Okay, and so it's quite, and this is maybe, you know, a very important point to note, is that these do interventions are not compatible with the kind of things that people know, you know, when you're working with distributions like marginalization or conditioning. So let's look at the following. Let's say we're doing an intervention on node x4. So we're setting x4, say, to 0. Okay, and we look at what happens to x3. Well, you know, what happens to x3? Well, x3 doesn't change at all, right? Because x4 is downstream of it. So the distribution of x3 when you change x4 is just a marginal of x3. Nothing happened to it. But note that, you know, a marginal distribution is in general not the same as a conditional distribution, right? In particular, x3 and x4 are certainly correlated. So, you know, the distribution of x3 given x4 is certainly different than the marginal distribution of x3. So note that this do operation is not the same as conditioning. Okay, it's important that we have a do here and that we don't just get rid of it. But let's look at it the other way around. Now we're going to intervene on x3 and we're looking at how x4 changes. Well, so now if we intervene on x3, x3 is upstream of x4. So certainly x4 changes. So certainly it's not equal to the marginal. But in fact, in this case, it's just the same as conditioning. Okay, so because conditioning is, you know, the same as just setting the upstream variable to a particular constant in this case. So you see that, you know, this do operation is something between conditioning and marginalization, but it's certainly not one or the other. It is really its own operation. And you can just, you know, you can figure out what the interventional distribution is just from the model itself. Okay, so that's a kind of interesting kind of new operation. I mean, new, it has already been introduced by Julia Pearl, but like a new operation when you think about distributions. And so now the problem that we want to really look at is, you know, we have observational data, meaning just data from this distribution here. And then we also have data where we go in and we actually set some nodes, say, to 0, or we applied a particular drug which had an effect on multiple nodes. Again, this is just an intervention. Right? And now all of this data we have together, and we would like to learn this graph. Okay, so we would actually like to learn the underlying causal graph. So the question is, how do we go about this? And what is known about it? Okay, so we somehow need to relate the distribution to a graph, right? To this directed acyclic graph. Okay, so one thing is maybe something that we can convince ourselves of. So if I have a directed acyclic graph like here, and this is my model, and if I took two variables that are not, like, say, for example, I don't know, x1 and x4, they're not connected by an edge, then if I condition on every one above, on all of my ancestors, then they will become independent, right? Because, you know, all of the information that x1 has about x4 comes in this case through x3. And, oh, sorry, in this case, x3 and x2, right? So everything that connects x1 and x4 comes through x2 and x3. So once you condition on x2 and x3, so all of the ancestors of any of these two nodes, they become independent, right? They don't share any information about each other anymore. So this is one way of going, you know, from a graph to statements about the distribution. But now we want to go backwards, right? We don't know the graph. We get samples from a distribution. So what we can use, or what we can learn based on this distribution, are conditional independence relations. And now I give you a list of these conditional independence relations. And the question for you is, can you actually learn the underlying graph? Can you actually learn the underlying directed acyclic graph just from these conditional independence relations? Now it is known that in general, there can be multiple directed acyclic graphs that satisfy exactly the same conditional independence relations. And in fact, these equivalence classes have been characterized in this work by Verma and Pearl, and you see them here on 3 nodes. And again, it is quite intuitive. Let's look at this first class here, that, you know, if all you get are conditional independence relations, well, for these two graphs, X and Y are correlated, And they're independent of z. But just from this correlation, you cannot tell whether x causes y or y causes x. Right? But if you would have interventional data, so if you would have the intervention on x, then these two graphs are actually distinguishable, because if I intervene on x, then in this graph, y changes. Whereas here, if I intervene on x, the distribution of y doesn't change. So if you also have interventions, then these equivalence classes become smaller, and that's also known. Okay, so it is known based on conditional independence relations, when you have observations or also interventions, how do these equivalence classes look like? They are known as Markov equivalence classes. And it's maybe quite interesting that, when I say it's known, there is actually a graphical criterion which tells you when are two graphs, two DAGs, directed acyclic graphs, in the same Markov equivalence class. And it's quite interesting. It's here. So as you kind of see from this little picture, they need to have the same skeleton, so the same adjacencies in the graph. And only some of the directions kind of matter, namely these directions here, which is known as an immorality. So these kinds of graph structure, where you have two nodes pointing towards each other. It's known as an immorality because you have parents that are not married that have a common child. So you see all this philosophy influence coming in terms of how things are called. Okay, so these kinds of structures matter. These are actually the ones that can be identified, and the others cannot. So graphical criteria are known. So this means in terms of learning the graph, this is all we can hope for, right? We will not be able to, just from the distribution itself, we don't have additional assumptions, we will not be able to identify these two graphs against each other. Because all we can learn is conditional independence relations. From conditional independence relations, we're going to try to learn this equivalence class of graphs. So that's really our problem, okay? So we know in the limit, this is all we can hope to learn in the best case. So now the question is, can we come up with algorithms that actually take in samples from the distribution, they learn these conditional independence relations, and then they output one of these equivalence classes. So in terms of algorithms, what is known? So there are really two types of algorithms, and two classes of algorithms, I should say, and within each there are multiple algorithms. I'm just here telling you about the most important ones or most prominent ones in these areas. So these two types of algorithms are really very different, and we'll talk about the advantages and disadvantages. So the constraint-based approach is super, both of them are very intuitive, but this one is that, the constraints are the conditional independence relations. And now we want to find a graph that satisfies as many of these conditional independence relations as possible. So how it works is, you have a list of conditional independence relations. Well, if there is an independence relation, there is certainly no edge. So for every conditional independence relation, you just keep removing edges. And then, you can identify some of these directions here by particular conditional independence relation. Okay, so that's, for example, the PC algorithm. I'll talk about advantages and disadvantages just afterwards. Let me tell you what the other approach is. So this is somehow a very local approach, right? For every conditional independence relation, I'm just going to remove edges. So you can already see that if some of the conditional independence relations are wrong, I'm going to make mistakes because I'm just removing edges and I'll never put them back in. So whatever mistakes I make, I'm just keeping accumulating mistakes. Score-based approach is different. It's now you want to do something more global. So I have a global score of a graph or an equivalence class, say, for example, a penalized likelihood score. I know that this, so if I were to enumerate all equivalence classes, there are multiple scores that are known to be consistent. So meaning they will be maximized in the correct equivalence class. Okay, this is one of them. But the problem is that there are so many equivalence classes or DAGs, right, that you cannot just enumerate them. So you want to do something greedy. And so this greedy equivalence search is one way of doing a greedy search over the space of Markov equivalence classes. And it's really a quite remarkable theorem that this approach, so what it does is it does one forward pass and one backward pass. So it starts in the empty graph, and then it just adds edges one at a time so as to always maximize the score. And then when you cannot maximize anymore, it stops, and then it removes edges one at a time until it cannot optimize the score any further. And then the equivalence class that is output then is provably the right one as the sample size goes to infinity. Because this is a really nice proof of like one forward pass and one backward pass is actually sufficient here. So both of these algorithms actually have guarantees, at least as the sample size goes to infinity. But you kind of already see the advantages and disadvantages. So score-based approaches in general, they perform better than constraint-based approaches. Just because, you know, whenever they make it's a greedy search. So you can kind of make quite a few mistakes along the path, and you usually still get to the global optimum, even though you're making some mistakes. Whereas constraint-based, whenever you make a mistake, you're just accumulating them. You can never get rid of mistakes. But of course here, this is a quite complicated and big search space. And I want to show you this on this next slide. So this is just, you know, these kinds of plots you'll see in any paper where they have some score-based and some constraint-based approach. It's just to show you that, you know, these score-based approaches, they always perform better than the constraint-based approaches. This is just one example of a paper where this has been done. And then this is kind of to show you, and I'm not going into it, but just to show you a little bit about, you know, this more algebraic and geometric problems that appear when you want to try to understand why, for example, the constraint-based approaches actually do so much worse than the score-based approaches. And it's really this problem of these conditional independence relations and how often you get them wrong. So a conditional independence relation corresponds to a manifold, okay? Corresponds to some lower dimensional manifold or algebraic variety. And so, you know, so the problem is these constraints, these conditional independence relations are learned from data. So if I don't have too much data, then many of these will be learned wrongly, right? I'll just, you know, conclude, I'll do a hypothesis test. We've heard quite a bit about it in the last talk. I'll do some hypothesis test and, you know, unfortunately there is some cutoff and I'll just say like it is, you know, it's going to be independent and with 5% or whatever you want to set the value, it will be a wrong, the test will actually conclude wrongly that you have some conditional independence relation. So the problem is that, you know, you really have to, in order to get the graph right, you need to be bounded away from all these manifolds, right? You don't want to get close to any of these manifolds which correspond to conditional independence relations that are not satisfied by your graph. But this is a plot for a 3-node graph. And here you already see, you actually have to be bounded away from all of these hypersurfaces. And so you see that there is very little space left for you to actually be bounded away from all of them, which then shows that, you know, in general, you will actually make mistakes. And hence, this is the reason why these algorithms usually don't perform so well. So there are a lot of nice geometric questions here, and I just have a reference there. And this is the other problem of, you know, I kind of said here that the score-based approaches, they do this greedy search over this huge search space. And I said that this is a, you know, probably a very big search space. And you can say, you know, we know how many DAGs there are. So the question is, are there also that many conditional independence relations, right? How large are conditional independence relations in general? Now, the interesting thing is that's actually not known. Okay, so this is a combinatorics problem, actually graph theory and combinatorics problem that is open. Although there is a very nice graphical description of what makes 2 DAGs be equivalent, it is not known how many Markov equivalence classes there are. So in average, how large these Markov equivalence classes are. What is known is from this completely computational work by Gillespie and Perlman, where they enumerated all DAGs up to 10 nodes, and they saw that there are about 10 to the 19 many equivalence classes. So this is a really big space where you're doing this greedy search. And so in terms of getting better algorithms, and that's what I want to get to, that you can then also use with interventional data, you really want to stay on the score-based approaches, right? Because they do better in general. But it would be so nice if you could kind of not have to run it over this huge search space and maybe have a much simpler way of actually searching among these. So you can imagine that actually moving between equivalence classes is quite a difficult task to do. And so the intuition for such an approach, and here you'll see how discrete geometry, discrete math and combinatorics and geometry actually adds or comes into causality, is a very, very intuitive approach. And I'm sure, you know, it will be something that you know, everyone here would think about as a first approach to do instead of these 2 other approaches that we've talked about, is the following. So, you know, so what is a DAG, a directed acyclic graph? Well, if I give you the skeleton, if I give you the undirected graph, and I also give you the ordering of the nodes, the permutation, well, then you get out the DAG, right? Because I just orient all of the edges according to the permutation. Now, so it is known, and maybe I go here first. So if I give you the correct permutation, it's actually very easy to get out the correct skeleton. And this is just based on this, conditional independence relation that I told you at the beginning, right? So every missing edge corresponds to the independence relation that the node is independent given everyone before. So if I tell you the ordering, well, I know who is everyone before, so I can then just get out the graph. So if I give you the correct permutation, it's very easy to get out the correct DAG, or to get out the correct undirected graph, and hence DAG. So the real problem is really just to find the correct permutation. It's not about learning the correct graph. And now I said that we don't know how many equivalence classes there are. There is no formula, right, on P nodes. But it is reasonable to believe that probably the space of permutations is much smaller than the space of these Markov equivalence classes. At least up to 10 nodes, it's certainly the case, and it's probably also the case afterwards, but it would be nice to actually have a proof. We don't have one. And so now the question is, how do we do a search over permutations, and can we find a score function that is going to be consistent if I just do a search over over permutations? And here is a result that tells you that, actually a very simple score function works, namely just a sparsity in the corresponding graph. So I have a permutation, right? And I have a corresponding graph, and my score function is just how many edges there are in this graph. And now if I were able to enumerate all permutations, then I just want to get the one that corresponds to the sparsest graph, or all of the ones that correspond to the sparsest graphs, they're all in the same equivalence class, and this is the correct equivalence class. That's what this result says, that we proved here. Now, of course, you don't want to enumerate all graphs, right, or all permutations. So then you do the next best thing, which is greedy search. So how does greedy search over the space of permutations work? Well, so we all know space of permutations is a polytope, right? It's known as the permutahedron. And so greedy search over the space of permutations, well, what would you do? You would probably just walk around these edges in the polytope. So you start somewhere randomly. So say here, I have a corresponding graph to it. And I look at my neighbors, and they also have graphs. And I just count how many edges there are there. And you look at them and you see if they're sparser, then you'll go there. Okay. And you continue like this. And what we proved is that, in fact, every local minimum is a global minimum, meaning you're not going to get stuck. Meaning that just by this greedy search over the space of permutations, you're actually going to end up in the correct graph. Okay. So, so with this, now, what we got here is somehow an algorithm that uses a much smaller search space, hopefully, it seems at least. And we can prove that it's provably consistent under weaker assumptions than the previous algorithms. And so this is also what you see in simulations. You actually usually get better performance, and also in terms of runtime. So we're not a lab that develops fast algorithms. So we have our Python implementation, and here are all the other implementations which have been highly optimized for running fast. So this you see the names are already fast, GS algorithms, etc. PC run on tetrate. And so these are the optimized ones. Certainly our algorithm is not as fast as these. But what you see here is that it can be run on thousands of nodes. And also, and this is work by Frederick Eberhard, who actually learns connectivity in the brain, so also causal networks in the brain. And you see that it's already faster than just learning an undirected graph in Python. Okay, so it can really be applied. All these algorithms can be applied to really many nodes. And this is in fact what we'll want to do. And I'll show you how this works in the COVID example. Okay, so we do have algorithms now that can learn causal graphs actually faster than what you can learn like these undirected graphs here, and that can be applied. In fact, and this I'm not going to go through, but all these algorithms actually have a version. It's just the same. It's just walking around the space of permutations can be applied also when you have interventional data. And in particular, maybe this is like where all the open problems are right now. What happens when you have latent variables? Because not always every node is observed. And so here, just to show you again, like the nice math doesn't end at permutations and polytopes. So if I have latent variables, then I actually don't have DAGs anymore, but I also have bidirected edges. So bidirected edges are not consistent with a permutation, but they are consistent with posets. So now what I have, so we have the theorem that says that the sparsest poset is the correct one. So now the question is, can we do a greedy search over the space of posets? Now, again, the space of posets is super nice. It's like before, the space of permutations was this nice polytope, the permutahedron. Now, the space of poset is in fact another poset. So I can use the relationships in the poset to walk along posets and try to greedily find the sparsest one. And that's what we do. And we have an algorithm doing that. And we have run it on thousands of graphs, and it seems to always have converged to the true one, so to the sparsest one. But we actually do not have a proof that this is really consistent, okay, that you cannot get stuck anywhere. So this proof is really still outstanding. And anyone who is interested in these kinds of more combinatorial questions and how this might relate to causality, we would love to have your input here if you've worked with posets, etc. together. Okay, so that's somehow where one is in terms of, learning, in terms of developing algorithms for learning causal graphs and how mathematics, different kinds of math areas like algebraic geometry and combinatorics, graph theory and discrete geometry, etc., can be used in this maybe, very disparate kind of field. And I'm going to apply these methods, all the way at the end to COVID-19. So that's kind of where we are in terms of actually learning these causal graphs. Now I want to just the last, I think I have about 10, 12, 15 minutes or so, talk about this other problem, which is, one is learning the underlying causal graph to actually be able to find the best protein drug targets. But we really also have this other problem, namely that, we have these drugs that are applied in one setting, and now we need to transfer them to a different cell type where they have not been applied. Right, and then there will be learning these networks, these causal graphs, etc. So how do we go about there? And now I'm going to change math. Okay, so now I'm going to go more into machine learning area. So if you come out of machine learning, if you are given such a problem, then you will probably have an immediate, kind of framework that you'll probably try to apply. And if you don't, then I'm going to propose what this framework here is. So this is known as style transfer, and I'm sure all of you have seen these really nice images where you have, you've taken a picture in the summer and you can run it through a neural network and out comes a picture in the winter. Okay, so this can be done usually by GANs, or I'm using a simpler framework here, which is just an autoencoder. So an autoencoder is just a neural network which consists of two parts, where you take an input, say an image, you map it to a latent space, usually lower dimensional. Okay, so we go from RD to RK, and then back from RK back to the input space to RD. Okay? And this neural network is just trained so that whatever you put in, you try to minimize the reconstruction error. Okay, so I want to get out something that looks like what I put in. So my training examples should be reconstructed as well as possible, meaning that in the latent space, I'm only going to keep all of the information necessary, right, in order to reconstruct the input-output. So think of PCA, but this is a nonlinear version of PCA. Okay, so now how is this used for style transfer? And here you see an example. This can also be done with faces. So say I have a whole lot of faces that I have as training examples. I have the neutral face and the smiley face. And I trained on them so that, when I put in this face, out comes the same face. When I put in this face, basically out comes the same face. So now I can look at where they land up in this latent space. So here I have the neutral face. Here I have the smiley face. So this vector here corresponds to making a face smile. Okay, so now how these things work, and it's really quite remarkable that this actually works, is you put in a new face. You don't have the smiley face yet. You want to generate it. So I put this in. I see where I land in the latent space. And now I'm saying, hey, let me just take this vector. Corresponds to making people smile. So let me move it over here and see what comes out. And so I look at this star and, a neural network. Now, this is a function, right? It learned a function from RK to RD. So I can take a new point and just look at what comes out. And in fact, out comes a smiley face. Okay, now this works actually really quite well. Okay, so, one has to understand why this works, etc. And I'm going to talk a little bit about that. But then the idea is quite simple, right? Maybe something like this will work with drugs. So if I have one cell type, I know what applying a drug does to it, right? I have this data. Now I have data from, this diseased lung epithelial cells, and I want to know what this drug does on it. Well, maybe I can just take this effect, move it over here, and predict that this is the effect that happens when you apply this drug. And this has been done in one paper just for 2 drugs, I think, in 2 cell types. And the question is whether this works in general. And there is a lot of reason from causality to believe that this shouldn't work in general. Okay, maybe I don't go through it, I just give the reference here. But now we have these large-scale drug screens, and the question is, well, we can test, right? Do they work in general? We have many drugs that have been applied to multiple cell types, so we can just test whether this kind of approach works in general. And so let's see. So I'll show you the drug screens, in fact. Okay, so this is this data that I told you. It's actually freely available, so anyone can play with it. It's called the CMAP data set. It's from the Broad Institute at MIT and Harvard. And so here's how the data set looks like. So you have many, many different perturbations, and you have about 70 different cell lines. Okay, and every entry is a 1,000-dimensional vector corresponding to gene expression. So you see that there are many, many drugs that have been applied. Many of them have been applied to few cell types. And then few perturbations have been applied to many cell types. So all of this white space here is data that has not been measured. Okay. And what you see here is just a UMAP projection of all of the data. And all I want to show here is that in color, you have the different cell types. And in black, I have the perturbations, and they're not colored by cell type. But it's kind of clear that the perturbations for a particular cell type, they get to lie inside the cell type. So the effect of perturbations is much smaller than the effect of being in a different cell type. Okay, so different cell types are much more different from each other than when you add a certain perturbation. Okay, so now you see here that there are some cell types that have many, many drugs applied to them, right? So I can just test this. So we can just predict, hey, let me figure out what is the effect, what is the drug signature, try to move it over in the latent space to a new cell type and see how correlated it is to the actual measured signature of the drug in that cell type. And that's what we'll do, and you'll see that the standard autoencoder framework actually in general doesn't work. Okay? So they were lucky in this kind of paper here. They were very lucky that it actually worked out. So this is the standard autoencoder framework. It goes from higher dimensional space to lower dimensional space to higher dimensional space. And all I'm showing you is here that basically it doesn't work. So what am I showing here? So I'm taking so all I care about is how is the drug signature that I'm predicting in the latent space, how well is it aligned with the real drug signature that I'm measuring, right? And I want this to be large, or either +1 or -1, right? So I want it to be either up here or down here. And you see that if I do this in the standard latent space, so like the standard autoencoders that people use and have used those in the previous paper, you see, you see that basically we're here along the diagonal, right? So basically it doesn't matter whether you're doing it in the original space or in the latent space, it's basically the same. And now here comes a new autoencoder that actually has never been used before. And I'll tell you the mathematics of why we even tried to use this one. It's completely unintuitive, but the math will actually tell you that this is the autoencoder you should be using. So this is a strange autoencoder. So I'm actually doing something that is maybe a bit crazy. So I'm going from input space to larger dimensional latent space to back to input space. Okay, so I'm not finding a lower dimensional embedding. I'm going to try to find a larger dimensional embedding. Now, this is not something people looked at because such a map could, for example, be the identity map, right? I have enough parameters here to actually just learn the identity map. And so, that's why usually you would go to a lower dimensional space, you hope to find some interesting embedding, right? And not something higher dimensional where you could just get out the identity map. And I'll give you intuition for it. And, we studied it in a paper, what is actually the map that is learned here. But, this is the larger dimensional latent space. And you see that here you exactly get out what you want. And you certainly see that it didn't learn the identity map, right? So you do have like these blobs here up here. So it certainly didn't learn the identity map. And, this is just a comparison to PCA. PCA does something similar, but it does it by just throwing away the whole signal, right? It cannot reconstruct anymore at all. Whereas here you can still reconstruct. Okay, so this means these kind of autoencoders are actually able to get the right structure out. They're actually able to align these drug signatures in the latent space, so that then maybe you can actually generalize them to new cell types that you have not yet seen. And I do want to give you intuition for, why are we using these kinds of crazy autoencoders? And so here is the intuition. So what I'm going to do is, and this is in this paper here that just appeared in PNAS. So here we have, so I'm going to do a very simple case. I'm going to go from R1 to R1. Okay, so this is an autoencoder that goes from 1 dimension to RD back to 1 dimension. So that's why I can represent it like this. Here are my training examples. Say I have 3 training examples. So I definitely have enough parameters to exactly map my training examples to the training examples. Okay? So definitely I will learn a function that goes through these points, because there will be no error, because I have enough parameters here to exactly map them from a training example to its training example. So the question is just, what does it learn in between? Okay, does it learn some crazy function? Does it learn the identity function, which would just look like this? Or does it learn something like this, which would mean anything is always mapped to one of the training examples? Or does it learn something different? Okay, so here comes the result. So what is nice is that these autoencoders go from RD to RD, right? So input and output dimension is the same. So what you can do is view it as a dynamical system. So whatever I put in, whatever comes out, I'll just put it back in, and I'll just iterate. Okay. So I have a trained autoencoder, and that's what we do here. It was trained on some images, and now I put in some new images with a lot of noise on it. And what you see, what happens is if you iterate it, right? At the beginning, something comes out that kind of looks very similar to what you put in. This is already after many iterations. It looks a little bit different. But then what you see is if you iterate and iterate, you're actually ending up in your training example. Okay, and here you see how often this happens. So I can add huge amounts of noise and still, I'm going to end up in my training example. So these basins of attraction are actually really quite large around the training examples. And this is also what we proved. I mean, we don't actually know much about the regions of attraction. That would be really interesting to know. But what we proved is that these training examples are in fact attractive fixed points. Okay, so the map that is learned is not the identity map. It's actually something very, very reasonable. So these, although they're highly over-parameterized, these maps, they learn functions that are self-regularizing. So they like to keep things that are similar to the training examples close to you. Okay, so they learn these kinds of maps, right? That are like, everything that's close to the training examples will be held close and made even closer. So they're attractive. And now, the question is, so this tells you that 0-dimensional points, they are attractors, right? Training examples are attractors. So, what was the intuition for this? Well, we just thought maybe, and we don't have a proof. We have the proof for 0-dimensional things. We don't have the proof for 1-dimensional things. But we're thinking that maybe 1-dimensional things that are similar will also be made more similar through this autoencoder, through an over-parameterized autoencoder. And that's in fact what seems to happen. Okay, we don't have a proof for this yet. This is something that we're actually currently working on. But it seems to be very helpful, right, to actually get generalizable drug signatures out. And so this is what we applied. And so now I'm getting actually to the application with COVID-19, and that's what I'm going to end with. So I have 3 minutes. So what you see here is, I do this exactly what we talked about at the beginning. I try to figure out what is the drugs, the signature of the disease. I now get all of the drug signatures. They're now generalizable across cell types. I'm getting them from the over-parameterized autoencoder. And here are just some examples of drugs. So I'm just trying to find the drug with the signature that is the most anti-correlated with the disease. And that gives me a list of drugs. Now, here you have a list of drugs. Now, what is already nice is actually these drugs, they're not just random ones. They're all kind of in the same family of drugs. So something reasonable is coming out, which is already a good first test. But in fact, all these drugs are drugs that are used in cancer. So they're very harmful for the body. Okay, so what you really want is to figure out, so these are actually also drugs that have many, many targets. So that's another problem with these drugs, and that's why probably they're also so harmful. So what you want to do is figure out of all of these protein targets of these drugs, well, which ones are actually the most relevant one for COVID-19? And then, there are more drugs than are in this drug list that we're here looking at in this particular data set. And maybe there are already drugs that are already approved and that are much more specific to this particular target that is actually the most effective, for this particular disease. And this would then be the drugs that we would actually propose. So we did look at all of these different drug targets that came out here and try to find which one is the one that is the most upstream of all of these differentially expressed genes. And now this is where, all of this causality analysis comes in. So the standard approach would just be like, I look at all of these targets, I see where they are in the network, and I just find the target that is the closest to all of these genes that are differentially expressed by the disease. But now that we can actually learn, right, these causal graphs instead of these undirected graphs, well, let's do that. And so the targets that we will output are the ones that are the most upstream from all of these differentially expressed genes in the disease. And so the one that comes out there is this RIPK1. It was a protein that I didn't know anything about before. And what is interesting is the same one comes out whether you do the analysis in these long cell line, which is one that is actually in this big drug screen, or in the cells that we actually have in our body. So you get out the same kind of protein that is the most upstream. Another kind of nice early validation is we know that COVID-19 is much more detrimental in the aging population than it is in young people. So you can actually build a disease network just for the aged population and without taking aging into account. Then you'll see that this protein will actually end up peripheral in the network if you don't take aging into account. And the last thing, also something we didn't build into our analysis, but what just comes out is that RIPK1 is quite interesting because it can actually directly bind to SARS-CoV-2 proteins. Okay. So this was found in a recent Nature paper. And now you can go about, well, trying to hypothesize what is the mechanism between it. And I don't want to say much, but this protein is actually super interesting. There are two different domains to it, and they actually have different outputs. So our hypothesis is that one is what happens in young people, and one is what happens in the older population. So in the young people, if this particular domain is activated, then what it actually turns on is immune response genes and survival pathways. On the other side, what it turns on is death pathway, so necroptosis, which leads to fibrosis and blood clotting, which is in fact exactly what you see as a pathology in these people who unfortunately died due to COVID-19. So this is, of course, something that we are now testing in the lab and needs to be tested. But I hope, this kind of shows you how, these causal inference algorithms, what I did is at the beginning provided a theoretical and algorithmic framework for integrating observational and interventional data, and then showed you how, and there, it was some types of math, and then also showed you how you can transport between different cell types, because that's also super important. Because now here we care about lung cells, and the next disease we'll care about lung epithelial cells, and the next disease we'll care about completely different cell types. So we need to be able to quickly move between different cell types. And here, this understanding overparameterization in autoencoders has really helped us to actually find a drug list that is, something that is reasonable. So I hope I was able to convince you that, a principled causal framework is really critical for drug discovery. And that's what is just coming out actually in the next week or so in Nature Communications. So with that, let me end and say, none of this would be possible without really great students and postdocs and, in fact, collaborators. In particular, on the biological side, I have worked a lot with Shiva's lab at ETH, and this is also joint work with Shiva's lab on SARS-CoV-2. And then the overparameterized autoencoder work is joined with Misha Belkin's lab at UCSD, and then, of course, all kinds of funding as well. And thank you all for your attention.
Thank you very much. So now we go to the question and answer. We have a little time. There is one question, Caroline, you can see it, I think, as well. So yep. Simon Brugia Paglia asked, thanks for the great talk. I was wondering if the self-regularizing effect in overparameterized autoencoders depends on the training algorithm employed both in theory and in practice. Is there any insight on this?
Yeah, these are great questions. So no, it does not in practice. Now, of course, how we prove these things is for gradient descent, so not even for stochastic gradient descent. So we prove it for gradient descent and initialized at 0. Okay. Now, usually in practice, what you do is you initialize as close as possible to 0, but you use stochastic gradient descent. What matters for actually the regions of attraction, these basins of attraction, is the activation functions you use. Again, we don't have a proof, but that would be really, really important to understand better is, you know, how do these basins of attraction depend on the activation function? And that seems to matter quite a bit. But these are great questions. Again, you know, how you see like geometry popping into these kinds of questions.
So here's another talk. Sorry, go ahead.
Also, Elena is raising the hand, but yes, and Teresa.
Oh, okay. Okay, let me ask, Teresa Crick asked the following question. Hi, Caroline, nice talk. Can I ask something about the number of equivalence classes for the causal graph? You said that not much is known beside the first cases. Can you say a little more?
Yeah, great question. So no, I cannot say more. So it's not known, meaning. Yeah, so it would be a really great combinatorics question to actually understand this. And maybe not even just to understand, I mean, this is already open, understand what is the number, but also what is the distribution. So as you see, you know, in this particular picture here, it seems like there are very few of large equivalence class sizes, and you know, most of them are very small. Okay, and they also did this when they enumerated them all. They found that in average, a Markov equivalence class is of size 4. Okay, while there are always these very large classes of p factorial, many elements, it seems that in average they are of size 4. And that about a quarter of them actually are this, like this picture here, they're small. They only consist of one member, meaning that you don't even need interventions to identify it. So it would be really, really important to actually solve this problem. So anyone who is interested in graph theory, combinatorics, I would love this problem to be solved.
Thank you. So Elena Robeva wrote her question. Have you thought about learning cyclic graphs?
Yeah, so these are another really great question. So, so there is work on the constraint-based setting by Thomas Richardson, who has thought a lot about cyclic graphs. On, you know, there are all kinds of algorithms, and I know Elena is aware of them, for learning cyclic graphs. Now, we have not thought about how to do these algorithms in somehow this setting. We have never thought about it, and it would, I think, be really interesting to figure out even what is the right, you know, what is the right representation of cyclic graphs. And that's, I think, always the most basic one is what is the right representation of the graph? And then can you prove this result? Namely that the sparsest one in that representation is the real one. And then the next step is, can you now show a greedy algorithm that will actually converge to that one? I think it's always these 3 steps, and I think the most important one is figuring out what is the right representation. And I would love for you to do this, Elena, if you can come up with something that makes sense. This would be really relevant for gene regulation, because of course there we do have, often should think that the graphs are cyclic.
Thank you very much. Yeah, I don't see any more questions. So thanks again for Caroline's nice talk. So this concludes the first online seminar of the FoCM Society. So the next one will be on February 26th, same time. It's always on the last Friday of the month up to the last one is scheduled for July. So thanks everyone to come, and see you in the end of February.
Thank you very much to the organizers for putting this together.
Thank you.
Bye.
Bye-bye.